one important property of scalar line integrals is additivity. And so this is basically what's going on here, is that let's suppose that we want to integrate over a curve C, where C is the union of a bunch of line segments, or not necessarily line segments, just, it's a piecewise smooth curve, but there could be sharp corners to it. So let's say that this is like C1, and this is C2, and this is C3. So if we have a scalar line integral over C of f of x, y, z ds, where C is the union of these line segments here, we can simply compute the scalar line integrals along each of these line segments. And then add them up, and that gives us our overall answer. So let's take a look at this example here. Integrate f of x, y, z is equal to x minus 3y squared plus z over the path from 0, 0, 0 to 1, 1, 0 to 1, 1, 1. Let's draw a picture really quick here. So let's see, x, y, and z. So 0, 0, 0 is the origin. 1, 1, 0 would be something like that, and the move there in the xy plane. And then 1, 1, 1, we'd be moving, up there. So 1, 1, 0, 1, 1, 1, 0, 0, 0. So here, how do we do this? We're going to, our curve here, we're going to break this into two chunks. Line segment from 0, 0, 0 to 1, 1, 0, and then the line segment from 1, 1, 0 to 1, 1, 1. So we need parameterizations here. So C1, let's say this is going to be from 0, 0, 0 to 1, 1, 0. We need a parameterization of C1. Let's see here. The z component stays constant at 0. The x component and the y component could both go from 0 to 1 in a straight line. So I think that T0 works here. There certainly are other parameterizations that we could give here. There's infinitely many, but this is probably going to be the simplest one that we can give. Meanwhile, let's just go ahead and say what's our parameterization for C2 from 1, 1, 0 to 1, 1, 1. Our 2 of t here. So let's see. Let's see here. The x and y component stay constant at 1. The z component goes from 0 to 1. So we use a t there, and we let this run from let t run from 0 to 1 here. By the way, note that I'm using t. This t is different than this t. That both of these parameterizations are going t from 0 to 1 here. And we're thinking of movement here. You might say, oh, this should be t from 0 to 1, and this should be t from 1 to 2. But it's completely fine, computationally speaking, to have reuse the same interval of t values here. We don't have to make that match up. We're going to calculate out these separately, add them together. This is fine. Okay, so let's go ahead and evaluate these line integrals here. So in order to do that, something that we would need, let's see, we need their derivatives for R1 of t and R2 of t. R1 prime of t will be 1, 1, 0, and the derivative here, the magnitude of the derivative would be the square root of 2. And R2 prime of t would be, the derivative here would be 0, 0, 1. And we know we need the magnitude of this, which is 1. And so then our scalar line integrals, the integral over C1 of f ds is going to be an integral from 0 to 1 of So what we have to do, we need to substitute in x and y are both t, z is 0 into here. So that would be t minus 3t squared plus 0. And then we need to throw in the factor here of the magnitude of the derivative of our parametrization, square root 2 dt. Okay, so this is our first integral. Let's see here. This is going to be the integral, antiderivative here will be square root 2 times t squared over 2 minus t cubed. Plug in t runs from 0 to 1. So square root 2 times 1/2 minus 1 is going to be negative root 2 over 2. Okay, now we need to do this over C2. Integral over C2 of f ds. Maybe integral t runs from 0 to 1. Okay, x is 1, y is 1, z is t. So 1 minus 3 times 1 squared plus t dt. And so this is the integral from 0 to 1 of negative 2 plus t dt. And, I really should be emphasizing here that, multiplying by 1 doesn't change anything, but really there should be the emphasis on that magnitude of the derivative being inserted in here. Okay, so let's see, integrating this would give us negative 2t plus t squared over 2, plug in from 0 to 1, and this is negative 3/2. So to give our final answer here, integral over c, where c is this piecewise smooth curve here, piecewise linear, of f ds is equal to integral over c1 of f ds plus the integral over c2 of f ds is negative root 2 over 2 minus 3/2. So that's showing additivity of scalar line integrals, and we'll see more additivity in the next section.